Hello, class. It's Sunday. We missed the September 17th class because we didn't have power in my part of Montgomery. So this Zoom video is to partly cover the missed class. I'm going to try to keep it to about 20 minutes, so we won't be able to cover everything in section 2.7. We can do more from 2.7 in Tuesday's class that's coming up. So the topic is nonlinear inequalities, but we're going to restrict coverage and just talk about graphing cubic polynomials. Now, keep checking your email and your Blackboard. Our first test is a week from Tuesday, not Tuesday coming up, but a week from Tuesday. It got rescheduled, pushed back one class meeting. I'll be making available a practice test for you this week. I might have had that for you by Tuesday, but certainly you'll have it this week. All right, let's see, 20 minutes. So we know a fair amount about quadratic polynomials already. So quadratic polynomials have the form y equal f of x equal ax squared plus bx plus c. And the key idea is rewriting f of x in HK form. So that form is a times x minus h squared plus k. So once you have this form, it tells you a great deal about properties of the function. So this will be a prominent topic on your first test. So cubic polynomials, have the form y equal f of x equals, so we have a cube term. Now, some of these coefficients could be 0, but this one can't be 0. If this were 0, we would have either a quadratic or a linear or a constant function. Okay, so we don't have an HK form for cubic polynomials. We're still interested in graphing cubic polynomials, and you'll learn more about that when you take Calculus 1, but we can say this. So quadratic polynomials have graphs that are parabolas, right? So you know what a parabola with a vertical axis. So whenever we have a quadratic polynomial, we know in advance the graph will look something like that. It could go down rather than up. The coordinate system might be anywhere. So in this case, the vertex is down here, that's the HK, and we have two x-intercepts. But they're various possibilities. The x-axis could be entirely below the graph, for example. What about cubic polynomials? Um, um, so what do their graphs look like? Well, the answer is they have shapes like this, or this, or maybe this. So they either go from minus infinity to plus infinity. In other words, they for large negative values of x, y is very, very negative and very large, or the reverse of that. But they, roughly speaking, they all have a shape similar to these here. But what we're interested in figuring out is when are they positive and when are they negative. So that depends. See, take this one for example. If this is the x-axis, then this particular cubic is negative, in other words, below the axis, up until here, and then it's positive. But if the x-axis were here, it would be negative here and then positive, but the x-axis could be here. So here it's negative, positive, positive again. So how do we know which case we have? And there's even a fourth case. If the x-axis were here, the graph is negative, positive. It looks like it's going to go negative, but it actually touches the x-axis and then changes direction. So all of those cases can happen. Let's see examples of them. Okay, so here's example one. So suppose f of x is x cubed minus 2x squared minus 9x plus 18. So you use synthetic division to factor, and it factors nicely, it turns out. So f of x factors like this. Okay, so we have three linear factors, and they're not repeated, they're all different. Three simple roots. Three, 2, and negative 3. And three linear factors, and they're all different. Distinct linear factors. Okay, so what's the graph like? Okay, so the graph crosses the x-axis in the numbers -3, 2, and 3. Okay, now we have 4 intervals here, and here's an interval, here's an interval, here's a little interval, and here's an interval. And on each of those intervals, the graph has constant sign. In other words, either it's negative for the whole interval or positive for the whole interval. To find out what's going on, you can take a test value for each interval. So pick a number less than -3, pick a number between -3 and 2, a number between 2 and 3, a number greater than 3. So for example, you could find f of -4. You could do this by synthetic division, for instance. And that turns out to be -43, -42, I believe. So when x is -4, the graph is way down here. So it comes up, goes through the number -3, and then it's positive. You can check that f of, now what's the simplest number between -3 and 2? 0, I would think. So f of 0 is just the constant 18, that's a positive number. So the graph stays positive from -3 to 2. And incidentally, we just figured out that this number here is 18. And then it crosses the x-axis again, and then between 2 and 3 it's negative. That's a rather tricky calculation. The simplest number between 2 and 3 is 5/2, and it turns out that f of 5/2 after some work is -11/8. So the graph dips down below the axis a little bit, and then beyond 3, the graph is positive again. So f of 4, for example, is 14. Now, this is simpler than I made it seem, probably. When you have 3 different linear factors, the cubic goes through the corresponding roots, those numbers on the x-axis, and each time it goes through a root, it changes sign, either from negative to positive or from positive to negative. So actually, as soon as I knew what was happening on this first interval, I didn't have to really do these extra calculations. It's going to go negative, positive, negative, and positive. Now, when you take Calculus 1, you'll learn a lot of more detail about. You figure out where this highest point is and this lowest point, and then there's something called a point of inflection here. That comes next semester. But all we care about in this section is knowing when the graph is negative and when it's positive. In summary, it's negative here and here, and it's positive from here to here and here. Next example. Okay, so this time f of x is x cubed minus 2x squared minus 7x minus 4. And after factoring, you get f of x is x minus 4 times x plus 1 squared So we have a simple root at x equals 4. We have a double root at x equals minus 1. Okay, now notice, no matter what numerical value I give to x, when I square x plus 1, I either get 0 or a positive number. I can't get a negative number. So this factor is never negative. It's always either 0 or positive. Always greater than or equal to 0. This factor here. So the sign of f of x is determined by the sign of x minus 4. So that means if x is less than 4, then f will be negative, and if x is greater than 4, f will be positive. So let's see if we can visualize the graph then. Okay, so here's negative 1, and here's 4. Okay, so to the left of 4, f is negative, and to the right of 4, f is positive. What happens at negative 1? Since this is a double root, the graph does the following. It comes up and touches the x-axis in negative 1, and it's tangent to the x-axis. It then changes direction. It's still negative, and it starts decreasing, and then it starts increasing, and then it goes through 4. So to the left of x equal 4, the graph is either below the x-axis or it touches the x-axis. And to the right of 4, the graph is above the x-axis. The second example. So the third one is f of x is x cubed plus 6x squared plus 12x plus 8. And after factoring, it looks like this. X plus 2 cubed. Okay, so the only value of x that gives us f of x equals 0 is negative 2. So we have a triple root at x equal negative 2. And the factor x plus 2 is repeated 3 times. X plus 2 times x plus 2 times x plus 2. Okay, so what about the sign behavior? Well, this is an odd exponent. So if x plus 2 is negative, its cube will be negative. If x plus 2 is positive, its cube will be positive, because that's an odd number there. So f of x is less than 0 if x is less than negative 2, and it's greater than 0 if x is greater than negative 2. What does the graph look like? Actually, we can use our shifting rule to graph this, now that I think about it. So we know the graph of g of x equal x cubed. That was one of our basic graphs that we had earlier. So one of our rules is if we replace x by x minus 2, we shift the graph to the left 2 units, rather than to the right. So here's -2, and the graph looks like this. It looks exactly like the graph of y equals x cubed, except that it goes through -2, 0, rather than 0, 0. So this is a triple root. And then the last example is oh man, I'm taking too long for this video. All right, so here's the last one. Now, so the squared term is missing. Now, when you use synthetic division to factor this, you have to supply a 0. For the x squared term. So you remember the rational roots of this function, if there are any, are divisors of -6. Turns out the only root is 2. So to verify that 2 is a root by synthetic division, you would do the following. 1, 0, -1, -6. So that's for the missing squared term. So you bring this number down, you multiply, add, multiply, add, multiply, and add, you get a 0 remainder. So how does it factor then? So since 2 is a root, x minus 2 is a factor, and the other factor is x squared plus 2x plus 3. Okay, now you'll have to, I'm taking too long here. You'll have to review what you know about, or should know about quadratic functions. So this quadratic doesn't factor over the real numbers. It's always positive. For any real number x. So once again, the sign of f just depends on the sign of this factor. So this time the graph is going to look something like this. So here's the number 2. And this is a simple root, by the way. So 2 is a simple root. It only occurs once. In the previous example, -2 was a triple root, but 2 is a simple root. So when you have a simple root, the graph, you need calculus to know this, but the graph is not tangent at 2, it just keeps increasing. So the graph looks something like this. I didn't do that correctly. Here's the number 2. So the graph just keeps going up. It does pass through that point, but it continually increases as we move from left to right. All right, so I'll rush through those examples. That'll at least get us started on section, 2.7, I think. Thank you.